Hi guys, in this video we'll take a closer look at covalent bonding, in particular hybridization and geometry. And we'll begin with looking at a fairly simple molecule, methane, a one-carbon hydrocarbon. Methane has sp3 hybridization, and we need to be able to show or graph that electron configuration. Okay, let's look at it. Here's my whiteboard. So we have methane, CH4, that's of course condensed. We have, well, let's just sort of spell this out. sp3 hybridization is what we're looking at here. Of course, we're just looking at the carbon. Hydrogen is never hybridized. Hydrogen just uses its 1s orbital. Hybridization is just a fancy word for mixing. We're going to be mixing the atomic orbitals. Okay? But let's start with this fact, real life fact. Methane, which by the way, let's show out a full structure. Carbon with 4 bonds, no lone pairs. But I'm not showing actual geometry or a correct geometry around this carbon. We'll get to that. Right now I just showed sort of 90-degree bond angles, but that's actually not correct. But there we have the bonds. And what we know about methane from experiment, that is from real life, is we have 4 identical CH bonds. Okay? Now, that's sort of the starting point. But let's go back and remember our ground state configuration for carbon. We had, and I'll just do valence, we had the 2s, yeah, and then we had the 2p. I'm not going to show the 1s, which is the subshell. 2p, they were 3p orbitals. And valence electrons, we have 1, 2, 3, 4. Okay, so this is the valence ground state, all right, electron configuration. But look at these orbitals here that we have. First off, we don't have 4 identical orbitals. We've got 3 p's and 1 s. You're not going to be able to make 4 identical CH bonds using 2 different types of orbitals. The other thing is, this looks like 2 electrons in 1 orbital. This looks like a lone pair of electrons. That looks like a lone pair of electrons. The carbon doesn't have a lone pair. So we've got some issues here in using the ground state configuration to explain the observed bonding. Now, most of what we're going to be talking about is theory. The theory, any theory is generated to explain reality. This is our reality. It's very hard to come up with any theory of using these orbitals to get to the reality here. So instead, the theory is, and actually the theory is supported by lots of evidence, when carbon starts doing covalent bonding, it doesn't bond using these original ground state atomic orbitals. It uses hybrid orbitals. It does some mixing whenever it goes into a bonding arrangement. All right, well, let's get there. By the way, something else we know about this, I say identical, they all have the same bond length. 4 identical CH bonds with all have the same length. You're not going to get the same length using a P or an S. They need to be the same type of orbitals. So, let's see how I can set this up. We want to go from here. I wish I would have turned it a little bit. I'll try to just go this way. And this means we're going to hybridize. We're going to mix, and we're going to generate a new sort of configuration here to work with. Now, important question to begin with. How many regions do we need around the carbon? How many bonding regions? Well, the answer is 4, okay? 4 bonding regions are needed. And as we go along and do more examples, hopefully this will become more clear. It's basically you got four single bond regions here. All right, now if you need 4 regions, thus we need 4 hybrid orbitals. Okay, I'm just going to say hybrids, but that means hybrid orbitals. 4 regions, we need 4 hybrids. Now, if you need 4 hybrids, how many of these original atomic orbitals do we need to mix? Well, the answer is simple and always the case. If you need 4, you need to mix 4. So all these are going to be mixed. All right? All mixed. Now I give you the analogy of like mixing ice cream. We're going to mix 3 scoops of P orbital ice cream and 1 scoop of S orbital ice cream. 3 scoops of chocolate, 1 scoop of vanilla. Put them in the blender, and what do we get? If you put all those different scoops into a blender and blend it up, you can then scoop out, well, what if we put 4 quarts of ice cream in? Then we'll be able to scoop out 4 quarts of ice cream. But it will then be blended, and all the scoops will then be the same. You no longer can scoop out just chocolate or just vanilla. Then we'll be able to scoop out a blend of the chocolate vanilla. Okay, that's the analogy. So we mix it up, turn on the blender, and pull something out. Now I'm going to actually, again, I wish I had more room here. I'm going to put these new 4 about right here. 1, 2, 3, 4. All right. Four scoops in, 4 scoops out. These 4, what do you want to call these? Well, they're just called sp3 orbitals. 4 sp3 orbitals. They're called sp3 because that's what went in. 1 scoop of S and 3 scoops of P. That's rather simplistic. All right. But now all 4 of these are the same. They have the same energy. Remember, this is energy scale. And importantly, the reason I wanted to draw them here is because the energy of these falls in between the P and the S original energy. Sort of makes sense. We're kind of averaging the energy of those 3 and the energy of this one. But let me ask you this. Are the energy of these going to fall closer to the P or the S energy? And the answer is, think simple. The answer is these are going to have energy closer to P than to S, mainly because 3 P's went into the blender and only 1 S went in. Just like chocolate or vanilla, if you put in 3 scoops of chocolate and only 1 scoop of vanilla, wouldn't the resulting mix be more chocolatey than vanilla? Yes. These hybrid orbitals have more characteristics of P than S. I put them on energy here, and we have now 4 sp3 hybrid orbitals. Those are hybrids, they're now mixed. Now we can put the 4 valence electrons here, following Hund's rule, 1 there, and the next one here, the next one here, and the next one here. Now we're ready to make 4 identical bonds. I can bring in an H with its electron, okay? I can put an X, before I did like a dot and an X, the X indicated the H electron. Here I'm going to indicate the electron from the H with an actual H. Electron from carbon, electron from H, teaming up in this, the carbon is using this orbital. 4 identical bonds to H. And that's what we have here. Now, I gave you the analogy of blending ice cream in a blender. What is really going on here? ultimately, a lot of this is based on mathematics, higher level mathematics. The theory is. We're not going to go there. So hopefully my analogy was useful. Let's see what else we can say. 4 identical orbitals, 4 identical bonds, sp3 hybridized. What do these orbitals look like? And how are they arranged around the carbon? First off, how do they look? Now we're mixing an S with 3 Ps. That's a little bit difficult. Instead, at this point, I'm just going to mix maybe an S. How about if we mix an S, which is a volleyball shape, right? And just 1 P. So there's the S. There's a P. Sort of mix them. Okay? Again, this is a very simple sort of description of what's going on here. Now the s orbital has a phase. We can call it just positive. Now the p orbital has phase, but if one lobe is positive, the lobe on the other is negative. Okay? Now here the S and the S is positive and the P is positive, so on this right side they're sort of reinforcing each other. And if we mix these two, here's the nucleus. And over here you get sort of a amplification of the two phases coming together, like if two waves in a lake came together and built a single larger wave. That's kind of what happened over here. But on the other side here, the positive of the S and the negative of the P are canceling each other, and that actually leads to a sort of well, over here constructive overlap, or this is destructive. This is like when two waves in a lake come together and they can actually cancel each other out if they don't come together sort of in sync. This can also happen with sound waves. You can actually have spaces where there's no sound because the sound came together and canceled each other out. And there's some audio tricks that you can do with that. But over here we get some canceling, but it's not completely. What you're left with is sort of something like that. And this is, because we only combine an S and a P, this is kind of an sp orbital. An sp hybrid orbital, what it looks like. Here's the nucleus. Now once we start drawing these around an atom, we'll only draw sort of the major lobe. This other portion on the other side is called the back lobe. And it's usually not drawn. But actually when we get to substitution reactions, we'll actually refer to that back lobe. And you may at that point not remember that it's actually there, because usually we're not going to draw it or discuss it. Okay, I'm not going to try to mix an S with 3 Ps. What we'll do is later on and in the handout, if you look on near the back of the handout, you'll see the different hybrids and we'll just compare them relative to each other. We'll get there. All right. Now, how are these 4 hybrids oriented around the carbon? Well, 4 regions. 4 regions spreads out in nature in a tetrahedral manner. That provides the most room for these regions. And actually, if you take four balloons and tie them together at the little tie part, they will naturally spread out in a tetrahedral arrangement. That's just sort of nature. The regions, the things that occupy the region, are looking for the most space. Okay. let's take a carbon here. Let's see if we can, how we want to draw this here. A carbon. And let's see if we can do this here. What's the best way? Well, first let's get to where we're going first, and then I'll back up. Where we want to get to is bonds in a tetrahedral manner. And I will always say 2 in the plane, okay, like this. And then 1 forward. And 1 back. And the one that's forward we draw bolded, and as we move away, it's like the H is coming towards you. As it comes towards you, it gets sort of larger. The one going away we do is dashed, and as it goes away, it gets smaller. Now let's back up and show this. Instead of a dashed for the 2 electron covalent bond, let's create these bonds by overlap of orbitals. Now, if I was in class, I'd maybe draw it and then maybe erase it and try to get it better. I'm going to try to do it good from the start here. 4 of these guys here, okay? And I'm not going to worry so much about the exact shape. Okay, there's 1. Is it okay if I don't put that back lobe there? Because if we put the back lobe, this is going to get more complicated. If I did, it'd be sort of here with the carbon representing the nucleus. I'm going to do 1, then I'm looking to spread these out in a tetrahedral manner. Now again, I think having this here helps. That's what we're getting to. Now this one here, tetrahedral, this one has to be forward. But you can't really tell that's forward on the paper, but if I put in sort of that projection, sort of makes it look forward a little bit. And then the 4th one, you see, back lobe, back lobe, back lobe, it would get a little crowded there with all those back lobes. The 4th one, and then where do you want to put the back lobe? All right, let's forget back lobe. I should have got larger and get smaller. I messed that up a little bit. Okay. Now let's just focus in on one of these. This is an sp3 hybrid. What is it interacting with in the molecule, which is here? Well, the H orbital. Covalent bonds come for interaction of orbitals. Hybrid orbital H. The H is using the 1s. 1s is just a spherical. And so that's supposed to be around. That's the H. 1s. And the magic is happening here. Let's draw in the 2 electrons. 1 electron like that, and 1 electron like that. There's 2 electrons here in these 2 orbitals. The 2 orbitals are overlapping to make that magical 2 electron covalent bond, which we rather simplistically illustrate with just the dash here. Okay, but when you see that, you need to know what's going on. All right, what type of orbitals are overlapping? sp3 to s. Now, we can just repeat that all the way around. I'm not going to write every little detail here and put the 2 electrons in there, but guess what? You got to, and if I could draw a circle, that would help. A spherical H, 1s. Okay? All right. And all this equals that when we clean it up. Now I started originally like this, but now you see this is a 90-degree angle if you took 9th grade geometry. But the actual is what? And we can see the angle best here. That is a 109.5. And so if these were the bond angles, things would be closer together. But nature, these electrons prefer to be further apart. Electrons repel each other. Of course, unless they are doing the magical bond, which requires some explanation. Why do these electrons want to come together? Again, that's a lot of information built into that there. Okay, we have more room here. This is tetrahedral / sp3. More room. It is 3D. Okay? If your paper's flat, you have one bond coming up and one going back. If it was on the board, like if I was in a classroom, 2 H's would be on the board, 1 H would be coming towards you, the other H would be going back behind the board. Okay? 3-dimensional. All right. Now importantly, what type of bond did we make here? This is a sigma bond. And a sigma bond comes from head to head overlap of the orbitals. All right? What does head to head mean? Well, what if I bonded these two together? Or I'll get two of the same, so hopefully they'll bond together. If I bonded these together, well, I could glue them together like that. That's not head to head, that's side to side. Head to head is like this, either that or this. And actually, hopefully, these will actually bond together head to head. All right? That's what head to head means. If you see these two, it's sort of, they're like just coming here, you know, head to head. Like hand to hand. Not arm to arm. All right? Now, these are bonded. A sigma bond can rotate. All right, look at these pins. They're bonded, but see, I can still, now the cap's not turning. If it did, it's going to kind of crinkle. But assume it wasn't crinkling in there and it would be a better demo, but it'll turn here, okay? And that's how a bond will do. You can just sit there and spin it. It still says connected. It's still connected, okay? It's still there, connected. Sigma bonds can rotate. Now we will see when we get to pi bonds, if they were connected like this, okay, like that, you can't rotate one. Because if you tried to rotate it, the bond is broken. It may be connected right there in the center, but it has to be fully side to side. If you do that, you just broke your bond. And it ain't going to want to do that. The bonding energy will keep it like that. Where over here, the bonding energy is not affected. This can rotate. The bonding energy doesn't prohibit this. Okay. Ultimately, for bonding regions, sort of led the way. Now, I may also refer to this as for electron regions. Okay. I think we said everything we need to say there. Let's move to sp2 hybridization. Also, I can check the outline. We indicated that. Okay. we graphed the hybridization here. We'll do more of that. It's rather simple right now. Next, let's do sp2 hybridization, and we're going to look at ethene, slang name ethylene. Somehow over the years that YL got sort of put in there and kind of slang. Okay. Ethylene, let's look at it. It's going to illustrate sp2 hybridization. First, the structure. It's a carbon-carbon double bond with just H's on each carbon. 2 carbons is eth prefix, and since it's an alkene, it gets the ene ending, and thus ethene or ethylene. Both carbons are sp2 in this case. And let's quickly remember our ground state configuration: 2s, 2p, energy of course, and okay. But again, this is, ground state is no good. Nothing there, right? Nothing. One of the most clear reasons it's no good is because we would end up with 2 lone pairs on the carbon. It doesn't have lone pairs. It exists in a hybridized state. Now, the first important question to ask is, let's focus in on this carbon. The other carbon is the exact same. How many electron regions around this carbon? All right. And that's 3. Single bond, double bond region. 3. 3 regions, thus we need how many hybrids? 3 hybrids. If we need 3 hybrids, how many of the original atomic orbitals do we need to mix? Well, if you put 5 in, you're going to get 5. If you put 3 in, you're going to get 3. We want 3, so we put in 3. You're always going to put in the S, but we're only going to put in 2 of the P's. So we're going to mix 3, and we're going to end up with 3 hybrids. All right. Three, what do you want to call these? Well, since we mix an S and 2 P's, we can call them SP, S and 2 P's, sp2 hybrids. 3 identical sp2 hybrids. But importantly, don't forget about this p orbital. We didn't mix it. It's still there. You can put it anywhere up here. I tend to do it a little bit to the side here. Okay, there's your p orbital. Draw a straight line. That's that one right there. Okay. Now the 4 valence electrons actually sit here. And actually, instead of pairing up here, we're going to put a 4th one up here. Three hybrids set your geometry. Okay. What geometry do you expect for 3 regions? 3 hybrids spread out in 3 regions. That is going to be 4 spreads out tetrahedral, 3 spreads out trigonal planar. Okay? Your hybrids is what sets your geometry. If you tie 3 balloons together, they will adopt a trigonal planar geometry and arrangement. All right? Now, I'm not going to try to anticipate and answer every question that comes up here. I will expect that you will ask, okay? I can think of maybe one question already that usually should be asked here. I'll let you do that. I'm going to go to, let's draw a carbon. All right. Here. Let's put this carbon here. And 3 hybrids around it. I'm not going to try to make these sp2s look any different than the sp3s, although they are. We'll look at those relative differences later. Here, I'm not going to put the back lobe. By the way, we're going to end up with boom, boom, boom. Trigonal planar. Okay? Everything is in the plane, planar. I'm just drawing the orbitals. If I did that trigonal planar, hopefully you agree that that is trigonal planar. I could have drawn that a little bit more. Okay. Downward. Now, this is, we'll mark this one up here, sp2. All 3 of them are sp2s. What is this orbital interacting with? Well, the H, the 1s orbital of the H, right? 1s. 1 electron from carbon, 1 electron from H. There's the magical 2 electrons that are interacting by overlap of these 2 orbitals. This is a sigma bond. Did we use the script of sigma? No, back over here. Sigma bond, usually written like that. All right. That is an sp2 to S overlap. Head-to-head overlap. Now, I have just same thing down here. I'm not going to repeat everything up there. It's identical. 2 identical CH bonds. But what's going over here? Well, this orbital is interacting with a carbon orbital. And the carbon orbital is the same exact setup as this carbon. They're identical. They're both sp2. If we put the other carbon over here and draw trigonal planar around it, we can go boom, boom, boom. Put in the orbitals that are actually arranged in the trigonal planar. And I could have drawn these both a little bit larger so they're actually sitting on top of each other, but what is right here? This is a sigma bond, a carbon-carbon sigma bond. That is created by overlap of sp2 and another sp2. And yes, there's 1 electron here. I don't really have a space to put it sort of shared. There's 1 electron in one orbital, 1 electron in the other. Okay. Now you can finish these up. There's H's over here. That's just like the 2 over on this side. All right. Again, trigonal planar. We can go ahead and put this here. Yeah. This is what we're going to get to, which is like up here. Only thing is I haven't got the other bond in here yet. It's not a double bond yet. How do we get the double bond? Well, we showed the 3 hybrids around the carbon. What else is there? P orbital. p orbital is not hybrid, it's a regular p orbital. How is it positioned according to these? It's actually perpendicular to that plane. If those are all flat, the p orbital on that carbon is actually half up and half above the page and half below the page. Okay. Now if this was on the board like this, flat on the board, half of the p orbital would be coming out and half would be going back behind the board. It's perpendicular or orthogonal to the plane to the sigma plane. I'm going to put it in here. I'm going to make the p orbital a little bit longer than the hybrid. In fact, it is. Why is the hybrid shorter than a p orbital? Well, because it has some s character. And s orbitals are little short spherical orbitals. That there. But the other carbon is the same, and I could have drawn that a little larger. It looks smaller. I should have drawn it larger. Okay. And there's one electron here, and there's one electron here, but guess what? These two orbitals are interacting side to side. All right? Those are interacting like this. And the side to side bond, orbitals interacting side to side to make a bond, is called a pi bond. Okay. Now this is only one bond, but we have electron density both above and below the plane. So even though I did two squigglies, that's just illustrating above and below the plane. That's one pi bond and one sigma bond. Okay. Which we indicated here. That was there. So head-to-head overlap between the two carbons, but also a side-to-side overlap, pi bond. All right. Ultimately, when you see an alkene, you should see one sigma bond and one pi bond. Always. Really, anytime you see a double bond. If you see a C double bond O, one is sigma and the second bond is a pi. All right. So over here, we just show that second bond as another dash. All right. But you gotta know what all this means. When you see this, you need to understand all this over here. All right. Trigonal planar, and bond angles here, here, and here are all the same, and they're all three equal 120 degrees. That's trigonal planar bond angles. So the HCH bond angle is 120 and the HCC bond angle is 120. Or the HCC interatomic angle. Okay, what else can we say here? Pi bonds cannot rotate. We've already said that. Yes, a pi bond is weaker than a sigma bond. Look, the side-to-side overlap, in my drawing, you see how far away they are? Now, in real life, those orbitals are closer than that. They have to be closer enough to interact to make the magical bonding. And so in real life, you know, it may be sort of, there's your sigma, and then the pi. I still can't make it fat enough that these start overlapping. Okay. I just have these far apart here. But they are close enough to interact. But still, we do need to know the sigma bond, the head-to-head overlap, is still stronger than a side-to-side overlap. And thus a pi bond is weaker than a sigma bond. Rotation will break Okay, so usually it will not rotate. What else can we say there? I see back up here, we never filled this in. The graphing the hybridization, what do we have? What type of bonds is the carbon making? It's making a sigma bond to H, a sigma bond to H, and a sigma bond to carbon. All right? Sigma bond to H, sigma bond to H, sigma bond to carbon. And then it's also making a pi bond to carbon. All right? And what type of orbitals do we use to make pi bonds? P orbitals. Hybrids typically make sigma bonds. And so my graphing is a sigma bond to H, sigma bond to H, sigma bond to carbon, pi bond to carbon. Altogether, what is that? That is your double bond. Okay, let's move to ethine. Ethine is a 2-carbon, of course eth, but it is a ine being the alkyne, and there carbon needs a 4th bond, and we'll have H's. And this is going to illustrate sp hybridization. They're both the same. The first question we can ask here is how many regions are around this carbon? Either one, they're both the same. Let's focus on this one. 2 regions. 2 regions is going to equal sp. How many hybrids do we need? Well, you need 2 hybrids. If you needed 3 regions, you'd need 3 hybrids. That was the previous example. We can go ahead and ask this. How are 2 electron regions going to be spread out the best way? And this is going to be linear geometry. Okay? If you tie 2 balloons together, they will spread out linear. Alright, if you tie them together at a little tie point, they'll just sit there like this. Alright? They will. If you ever tie 2 balloons together and they're like this, please let me know. They're not going to do that. Okay. Well, ground state configuration, 2s, 2p. And I see that I've been doing ground state configuration wrong. Yeah. This should be over here. Doesn't matter for what we've been doing. Did I do it wrong over here? Yeah. What rule did we break there? I say we, I should say I. I think that is we fill degenerate orbitals first before we start pairing. What is that? Is that Hund's rule? Is that right? I haven't had Gen Chem in a few years. All right. We need to get 2 hybrids, so we're going to mix 2, and we're going to get 2 SP. We call them SPs because that's what we mix. We just want to mix an S and a P. 2 sp2 hybrid orbitals. And we can't forget the other 2 p orbitals that are left over. All right. Okay. Let's get to a carbon. 2 hybrids are going to be spread out linear. I'll start with just bonds linear, okay, to help me. Although this gets easier when we only have 2. There's one here. Again, I'm not going to try to say, you know, the shape of these yet. We'll get to that. I'm not going to do the back lobe here, because over here I'm actually going to leave the room for the other one. That's not a p orbital, that's two sp2 hybrids, sp hybrids with no back lobe. What are we trying to get to? Trying to get over here. This is an sp. What is it bonding with? Well, the H, 1s, one electron from H, one electron from carbon to make sigma bond. All right. Yeah. Well, how about over here? Well, this carbon's bonded to another carbon. The carbon's the exact same. Hybrid. Hybrid. I'm running out of room. sp. One electron from this carbon, one electron from that carbon. Of course, that's sp also. That's sp. What do you have here? sp, sp, sigma bond. There's an H over here. Okay. Same as over here. But what else is on this carbon? Not one, but two p orbitals. All right. The first one is in the plane of these. Boom. Boom. I tried to make it a little larger, a little longer than the hybrid. Indeed it is. The other carbon's the exact same, so we're just duplicating that. And one electron, and these are interacting side to side. Pi bond, of course any pi bond is going to be pp overlap. What else is on this carbon? Not one p orbital, but two. The other one is perpendicular to that one. That is, if that one's flat on the paper like that, the other one is like this. Okay? Or if that one is up, then that one would be flat. Now, of course, there's electron density on both sides. It's kind of like, okay. They're orthogonal. The best way to show this, is very difficult to show this, and we'll have to look at pictures in your textbook, is to kind of throw another one on here. Sort of like this. And it gets a little convoluted, but maybe I can use, now this orbital is interacting with that, and this orbital is interacting with that. And that is another pi bond. It is essentially, you got two p orbitals flat, those are interacting side to side, but then you also have two p orbitals on each carbon like this, you know, perpendicular, and those are interacting side to side as well. So you got a 3D going on here. So there's two pi bonds there, and of course each pi bond we just show simplistically as another dash, and we get to that, which was the original. But anytime you see the triple bond, you see 1 sigma and 2 pi's. You got to see that. And then again, please see your textbook for illustration of this. We may have time to show it in class. I'm not going to try to show it here in the video. Ultimately, graphing the hybridization, what type of bonds do you see here? I see a sigma bond to H. So 1 electron is interacting with the H electron, 1 electron from carbon interacting with H electron, makes sigma bond to H, and then sigma bond to carbon. Okay? Sigma bond to H, sigma bond to carbon. That's in here. What else do we see here? Pi bond to carbon and pi bond to carbon. Now this graphing is just 1 carbon. If you wanted to graph the other carbon, well, it would be the same exact setup. But here, the electrons are from the carbon and this carbon, and the H is that H, and 3 bonds to that carbon. So the triple bond is a sigma bond and 2 pi bonds. Linear. All right. Hybrid set the geometry. This bond angle here is 180 degrees. Comes from a linear arrangement of the HCC. What else can we say here about the alkyne? Okay. Ethine. Let's look at bond lengths and bond strengths. This is going to be in the functional group DUS handout. And we get back here, there's actually some, maybe here, what we just looked at with the triple bond. Now this is not in color. Sometimes in your textbook the colored version will be easier to kind of look at. Shows that sigma bond there and then the 2 pi bonds. Okay, that's not 4 pi bonds. Each pi bond has electron density both above and below the sort of the sigma framework. Okay. What I want to look at to end this video is the back of this handout, functional group DUS handout, where we look at, I show you the relative differences between the different hybrids. All right, I'm showing the back lobe, but which one is longer? Well, obviously sp3. Why is sp3 longer? Well, let me say this. Why is sp shorter? Because what went into the blender here? 1s and 1p, right? 1s and 1p. Got mixed. This is 50% s. Here, 1s and 3p's. So this is only 25% s. And this is what? 33% s. Like 33% vanilla and 66% chocolate. But this is how it's usually referred to. More s character. The more s character, the more it's going to resemble an s orbital. And an s orbital is Well, the s is shorter and rounder. Okay? If you go here, which one went further away from the nucleus? The p orbital goes further away from the nucleus. The p orbital is more elongated. P orbital is longer. So the more your hybrid has s character, the shorter it's going to be. The shorter and rounder it's going to be. And so I'm trying to actually show this shorter but also rounder because it's 50% s. As the s character decreases, it gets longer and not as round. Longer and not as round. Now if we went to just 0% s, that would be all p. Well, the all p would be even longer. Okay? Of course, if it was all p, it would have the lobe over here. You only get the back lobes when you hybridize. All right? So, hopefully you get that. Understanding this, understanding percent s character helps you understand the lengths of these. But it will also help you understand the energy and bond strength. All right? Your SP makes stronger bonds. Because it's more S character. Back over here. Which electrons are more stable? Those in P or S? Well, those in S. They're lower in energy. Lower energy electrons are going to make more stable bonds. All right? The more S character, the lower in energy the hybrid is. And thus it's going to make stronger bonds. And shorter bonds. And typically shorter bonds are stronger. I don't know if that's always the case. Okay. I may end this video here. We'll pick up in the second video on hybridization by looking at table 1.7 here, which is from the Smith or Bruce textbook, and we'll look at sort of a summary of bond angles, bond lengths, bond strengths. But it will hopefully be pretty clear if we consider what we set up here. Percent S character will help us. Then we can answer certain questions like down here at the bottom. And in the next video, we will also look at other hybridization examples, including some ions and atoms other than carbon. Now, when we get to atoms other than carbon, the discussion will be no different. But we will have atoms that have lone pairs, and we'll have to learn how to deal with them, including when the lone pair may be in resonance. But I'll end this video here and pick the discussion up in the next video.